Hello everyone, this is Doug, and in this video we're going to talk about those anhydrides, how we use them as acylating agents, and I'll give you a couple of examples of reactions that use them. I want to mention right here at the top here, right, so I wrote down common reactions of anhydrides. You'll also hear these called acid anhydrides. Same thing. So if you're looking around online or you have a different textbook or something like that, anhydrides or acid anhydrides are the same thing. Now, just to remind you, where we're falling in our sort of reactivity ladder here, we're talking about the anhydrides, these suckers, right? So they're not quite as reactive as acyl halides, or also known as acid halides, but they're quite reactive, right? Much more reactive than esters and amides and nitriles. And again, remember that anhydrides are so reactive that even something like water can hydrolyze them, right? You don't need to add strong acid or base or anything like that to hydrolyze these. They're super duper reactive. So even something just like water, right? If you want to turn these back into carboxylic acids, even something like water, which again, like I mentioned in the different videos, why you don't see anhydrides in any natural products, right? Because all living organisms are water-based. That would immediately react to anhydrides. So you don't see them in any natural products. They're pretty much they only exist for chemists as reagents to acylate things. Now, a note about forming them here. Like I was saying, they only exist really for chemists, so we usually just buy them from a company. I've never made an anhydride. I don't know of anyone who has made their own anhydride. You just go to Sigma Aldrich or TCI and you just buy your, benzoyl anhydride or your acetic anhydride or whatever it is that you want, right? And also when we buy them, they're almost always symmetric, right? So like, for example, if you get an anhydride, it's almost certainly going to have the same two groups, right? So this would be acetic anhydride. It's symmetrical. There's a methyl on either side. You don't normally get like a mixed anhydride. They exist. There's no reason why you can't have a mixed anhydride, but that's asymmetric. And these are rare, right? There's not a lot of good reasons to use these, whereas the symmetric ones are super common. And that's just so you don't have to worry about accidentally getting a mixture of products. In chemistry, we want to get the best yield, the most of what we want. So we use symmetrical anhydrides so that we can have just one option of actually acylating the thing that we want. If you did want to make your own, though, you got kind of two methods here, right? We can make them from the carboxylic acids themselves. So if I did want to make something like, let's say, the benzoyl anhydride, I could take two equivalents, right, of benzoic acid, and you can either just heat the bejesus out of it, and that will drive off water. You're going to remove water. Let me make that a little bit prettier. Right? So you can remove water. That would be taking an H and an OH from the two molecules, hence since it's called an anhydride, right? We're removing water. It's anhydride. And that would give you your anhydride. And now the important idea here is that this water would have been boiled off, right? So that it cannot react with your very, very, very reactive anhydride. Another route is you could have used a dehydrating agent. So a common one is P4O10. It's just a dehydration agent. A dehydrating agent. And again, that would form the same product there. You'd get the same anhydride. Again, people don't tend to make a lot of their own anhydrides. We just buy them. But if you had to make them, here are the two ways that you would make them. For me, honestly, I'm probably not going to ask you how to make them from carboxylic acids just because, again, people don't do it. You could also make them from acyl halides, though, right? So if I did have an acyl halide, you could add, for example, right, CH3COO minus, right? I could add a carboxylate salt, and then that would just do the typical addition-elimination reaction that we would talk about, right? Where your minus would attack the carbonyl of one thing that kicks up, and I'm being lazy, so I'll do this in a different color to show the elimination step, the second step. Don't do what I'm doing, right? Do as I say, not as I do. Right, there'd be an intermediate, and then the electrons from the oxygen would drop down. But the point is that you would have substituted that chlorine for that carboxylate, which would give you that anhydride, this would be a mixed anhydride in this case, and then NaCl. Right, so we can make them from acyl halides, again, because acyl halides are higher on that reactivity ladder, so you can turn them into anything below them, including a acid anhydride, including an anhydride. So those are the two ways that you would possibly make them. Again, we just buy them. Now their general reactivity, like I was saying, they're super reactive, right? So here in the middle, I've got my anhydride. And I could do my good old hydrolysis. And like I was saying at the top of this video, it's so reactive, you can use just water to hydrolyze it back to your carboxylic acid. Easy breezy. In fact, it's so easy breezy that whenever you're working with anhydrides, you have to make sure everything's really dry, right? The drier, the better. Or you need to use a huge excess of anhydrides so that it sort of scavenges whatever water's on your glassware, and then you eventually try to make what you want to make. You could add just an alcohol to turn something into an ester, right? So if you just simply expose to some sort of alcohol, your alcohol is going to add in, do that additional elimination, and you'll make an ester. Or if you want, you can make an amide fairly easily by, again, just adding excess, right, of whatever amine you want. Again, this could be ammonia, right? It could be just good old NH3. Or this could be a primary amine or a secondary amine. Right? It just cannot be a tertiary amine because you have to have an H on here to lose at the end, is the idea. So anhydrides can be used to make esters, amides, or you can hydrolyze them back to carboxylic acids. So what does this mechanism look like? Now I will more properly draw out the real mechanism here. I'll do it in all of steps. So let me put my lone pairs on here just so I can be consistent. And I'll put my partial charges on here just so I can start thinking about what might react with what. Partial negative, 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 positive, positive. Now we already know the general reactivity, right, of all of these derivatives. They're all addition elimination steps. So my first thing is I'm going to have my nucleophile, even though it's just an alcohol, it's a poor nucleophile, it's still nucleophilic enough to attack these really, really reactive anhydrides. So in your first step, we're going to have our phenyl still there. Now we have an O minus, right? Those electrons were kicked up because the pi bond's the weakest bond. I'm going to keep all my alone pairs. And I've added an O with that cyclopentyl group, a hydrogen. And now that oxygen's positive, right? Because it gave away electrons. And this is that point again where I don't care if you deprotonate the oxygen first or have those electrons drop down first, whichever one is totally fine by me. But again, this negative O, we want to ask ourselves, can these electrons drop down and kick something out, right? Is there something that's even remotely a good leaving group on there, or even a decent, even anything remotely stable? Definitely not going to kick out the phenyl because that would be a C minus. I could kick out my O plus. That's a great leaving group, right? Which is why I say that this can go backwards. Let me erase this to emphasize, right, that we're saying that this can go backwards if I kicked out the cyclopentyl alcohol group. Or I could kick out this group, which would be the best of the groups because it would be a negative O, which is great, but resonance stabilized, right, which is very stable. And so if I take a look at that, now I have the pH. I've remade that double bond, right, because I had those electrons drop back down. And now I have an O with the H cyclopentyl group that was positive. And I have a CH3 double bond O, O minus. And then probably this H is just getting deprotonated, right? It's going to end up on what would now be acetic acid. And you make your product, right? So I've got the phenyl group, an oxygen, an O, and my cyclopentyl ether, right? Plus the acetic acid. Oh, it's not acetic acid. Sorry, it's benzoic acid. You guys got to keep me on my toes. Right, I accidentally put a methyl there. It's not acetic acid. It's benzoic acid. So phenyl group, right? That'd be benzoic acid. Is the idea, right? And again, I went from taking an anhydride, which is very reactive, and I went down to forming an ester. And so this mechanism would be identical if I was trying to make an amide. It would be identical if I was trying to hydrolyze it, right? I'd just add water instead of an alcohol. It would be the same mechanism, only I'd end up with two benzoic acids. So this is just your general reactivity for all of the reactions of acyl halides. Now, the two main uses, you actually have already seen anhydrides before. We didn't talk too much about their reactivity, but we did look at them when we had our Friedel-Crafts acylations, right? Remember with Friedel-Crafts acylations, we used either the acyl halides, which are probably the most common example, or an anhydride. And we actually did this one in class, right? I don't know if anyone remembers this, but this is where we took ferrocene and we made acylated it, right? We made acetylferrocene. And what we did, right, was we added acetic anhydride. And we added an excess of it. We added phosphoric acid as a catalyst here. That's just a catalyst to help us make that acetic anhydride a little more electrophilic. And again, if you don't remember, I may have mentioned this in a previous lecture, but acetic, right, that ace piece, that just refers to a CH3 double bond O and then whatever, right? Whatever is coming off here can be kind of anything, right? So acetic acid is when there's an OH there. Acetaldehyde is when there's a hydrogen there. Acetamide is when there's an NH2 there. But that ace piece refers to that 2-carbon piece. And you'll learn more about this when you talk about like acetyl-CoA anyways, I won't go too much into biochem, but that ace piece is usually that 2-carbon piece. This is what we're talking about. So acetic anhydride is a common name you'll see. We can also use these reagents to acylate alcohols or amides, right? You might call it acylating an alcohol or amide, but it's really just doing the reaction that I did on the previous slide, right? So you're just trying to add an acyl group here. So again, in this case, I use the same acetic anhydride. So I know I'm just going to take this piece and I'm putting it on the oxygen. That's all we're really doing here. So I've acylated it. This is an example of taking salicylic acid and making aspirin, which is a really common organic chemistry lab. You just add in acetic acid, stir it around with the salicylic acid, and you get aspirin. Really high yielding, really easy to do. The leftover acetic acid is really easy to get rid of, and then like you've made some aspirin, which is kind of fun. So these are the two main purposes of your anhydrides. So let's look at some examples. So here in this first one, right? Oh, actually, you should probably pause, see what you can do with these. So go ahead and pause here. I'll give you a sec. See if you can figure out what the products are when you add these different acylating agents or these different anhydrides. Okay, for the first one, it looks like I've got an amine and I've got an anhydride, so I know I'm trying to make an amide. And since this is acetic anhydride, I know I'm just adding that acyl piece. So I'm just going to redraw my amine. Got a nitrogen. I'm going to take off one of the hydrogens and replace it with whatever was on that anhydride. So in this case, the acetyl piece. That's just a 2-carbon piece, carbonyl CH3. That's it. Over here, I have a benzoyl anhydride, right? So I've got phenols on the end instead of methyls. Doesn't really change too much, right? This is still going to be an acylating reaction. I've got an alcohol. And I know, so that means I know I'm going to make an ester. And so I'm just going to take whatever that acylating piece was and put it on my alcohol, right? So my alcohol was this guy. And now I'm just going to add double bond O with that phenyl. So now I've made the benzyl ether, or the benzyl ester, excuse me. That's it. And then there'd be the side products. I know I don't draw the side products very often, and that bugs some people, right? You'd have benzoic acid as a side product, or you'd have acetic acid as a side product. Either of those. This one down here, I don't see anything to acylate, like to make a carboxylic acid derivative, so this must be right, because this is just toluene. So this must be an EAS reaction. So I'm just doing a Friedel-Crafts acylation here. And so I'm just going to follow my electrophilic aromatic substitution rules, right? So I know that this is an orthopara director, right? Because it's a methyl group, it's an alkyl group. So I'm just going to go ahead and slap my acyl group para. I would also get some where there's ortho. All right, so here I'm doing a Friedel-Crafts acylation. And I recognize that because I don't see any good nucleophiles on toluene aside from the actual aromatic ring itself, which is why the aromatic ring goes and attacks my anhydride to acylate it. And then lastly, I have this reaction down here. This is a common one for sugar chemistry, right? This is glucose, specifically in its beta form, but that's irrelevant. We'll talk more about that later. And here, see that AC? Again, that AC stands for acetyl. And that acetyl is that CH3, double bond O, whatever piece, right? So that acetyl piece. So AC2O is the CH3, C double bond O, O, and then another AC group, another acetyl group. So it's the same reagent that I had up there, just written out a different way and using a really common abbreviation. But what you see here is, I already drew the product, but you just add AC to every single thing, right? So this is just a whole bunch of esters. You just put esters all over this place. All the alcohols became esters. Notice that there's excess of this stuff. This is a common reaction that you see with sugar chemistry stuff, that if we get to sugar chemistry, you'll for sure see too. So here's just some examples of using anhydrides. Again, they're things that we usually buy and we use them as acylating agents. Whether we want to do that to an aromatic ring or alcohol or an amide is kind of the chemist's choice. So do some practice problems. I hope that answers your questions. Happy studying.